Okay, so going back to our discussion, here's our reference, and it has applications. I mean, you just have to read the description right here for the applications and also the definitions, because I will include that in the exams. And for the types of flat belts, we have discussed this, that the flat belts, it has, or it's rubberized. I mean, it mentioned only two types: the rubberized fabric and the nylon cord. Okay, and here's the description and the specifications. Okay, so let's go through the tables. Table 1, it says here the power rating of rubber belts, and this is watts per mm of belt width. Okay, so you would notice right here we have this belt speed in meters per minute. That means that this is the linear speed. And right here we have the number of plies, and you would also notice the number of ply if this is the type of the material, if it's fabric belt, or if it is a hard fabric belt or a rayon cord belt. Okay, and here's the number of ply: 3, 4, 5, 6, 7, 8. And what you can obtain right here is the power rating of rubber belts, which is in watts per mm. Okay, so we'll use this table when we compute for the belt width. Okay, and for the table 2, it says here minimum pulley diameters for rubber belts, and right here, here's the belt speed, linear belt speed, and right here is the number of plies. Okay, so for example, we have this 610 meters per minute, and we want to use the 3-ply belts. Then the minimum diameter for the pulley would be 102, which is 4 inches. Okay, and the next one is this table number 3. This is the minimum and maximum plies of rubber belting. So we have here the width of the belt. This is 5176 102. This is if you convert this to inches, this is just 2 inches, 3, 4, 5, 6. What is this? I think this is 8. Okay, 8, 9, and 10. Sorry, 8. This is actually 10. This is 10 inches. This is 12 inches. Okay, so if that's the width, that's the available width, and here's the minimum number of plies and the maximum number of plies. Okay, so take note that these are just based on this standard, but in practice, then of course you would want to also check that in the manufacturer's catalog. Okay, and another type of belt is the nylon cord, and we have this table right here, table 4. That's the power rating of section light capacity nylon cord belts. Because for nylon cord belts, it's further specified as light, medium capacity, and heavy. Okay, so that's table 4, 5, 6, and you see here's the RPM. Right, here's the RPM of smaller pulley. So take note, this is RPM. The other one was in terms of linear belt speed. Okay, and here's the diameter of the faster pulley. Then what's going to be the power? However, this was given in terms of watts only, not watts per mm. Okay, what else? This table 7, you just have to check the thickness, the minimum allowable diameter, recommended diameter, and the width right here. So if we have a light capacity section, then what's the available width? If you have a medium capacity, here's the available width, and that's in mm. Okay, and belt length. So I've mentioned to you that I think they are referring to endless nylon cord belts, because right here it says, okay, for markings of the belt, we have to specify the type of belt and its width, and for endless nylon cord belts, length is indicated. So that means that it has a specified length already. Okay, and here it just says if you have this asterisk sign, then that means that it indicates that such length is available. Okay, now let's fast forward here to figure number 2. There is a figure right here that says flat cord belt selection chart, and this is something similar to the V-belts, V-belt drives, or V-belt selection charts. How do we know if we have to use the type A, the type B, or type C? So right here it says we have here the horizontal axis. It's the design power, and it's given in watts. So take note, design power, that means that we have to multiply the rated power to the service factor. And the vertical axis is RPM of the faster pulley. Actually, it says small pulley. Okay, but for some catalogs they use faster pulley. Okay, so you just have to project a line, and you have this FL section, FM, and FH. So that stands for the light capacity, medium capacity, and the high capacity. Okay, and this is just for nylon cord. Okay, what else? For the service factors. Now, for the service factors, so here's the application, and here's the selection of the type of the prime mover. So right here it says squirrel cage AC motor. So these are electric motors. This one is a diesel engine, 4 or more cycles above 700 RPM. So here's the type of electric motor. So we have wound rotor AC motor, or single phase capacity motor, or DC shunt. So there's a list of values for the service factors. Okay, so I guess that's enough, and we'll do our first sample problem. Okay, so for this first sample problem regarding the Flatbelt drives, this one is taken from the reviewer by AD Bologna. It says here that the drive shaft of an engine is driving the rice mill line shaft that drives a 24 inches flat pulley in a cross drive assembly. Okay, and the drive shaft pulley has 6 inches in diameter. The distance between pulleys measured from the center of the shaft is 20 feet. What would be the length of the flat belt needed for the drive? And also add 1 foot from the computed belt length for splicing purposes. Okay, so since we don't have the figure, then it's also helpful if we draw, or if we convert this statement into figure. And it says here we have 24 inch and 6 inches, right? So let's write it here, or let's draw. Okay, illustrate. Okay, illustrate the statement or the problem. Alright, so right here we have 24 inches. Oh, sorry, that's not. That's this one is an open drive, so let's not use that. Sorry about that. Right, so here it is. So here's our drive system, and that's right here. This is 24 inches diameter, and this one is 6 inches diameter, and the center distance, right, this one is 20 feet. What else? I think that's enough. So solving now for the belt length. Okay, so recall that the equation for this is just simply L sub B. The belt length is just equal to 2C plus pi over 2, right, plus D1 plus the diameter of the driven plus what's your D1? I think this is D1 plus, right? Because the minus sign is for the open drive, right? D1 plus D2 squared all over 4C. Okay, so we just have to substitute all the values and we can obtain the belt length. So 2 times 20 feet plus pi over 2, okay, plus 24 plus 6, this is 30 inches, plus 30 squared all over 4 times 20. Okay, so 2 times 20 plus 30 squared divided by 80. So we have 98.37. This is 98.37 feet. However, it says here that add 1 foot from the computed belt length for splicing purposes. So this is LB is equal to let's say 98.37 feet plus 1 foot. So this is just simply 100 feet. Okay, so I think that's all for this problem number 1, and let's go to problem number 2. Okay, so for this second problem, this problem is actually taken from the PAS, and I mean PAS sample problem at the back part of this PAS number. And it says here, assume a normal torque squirrel cage AC motor for a centrifugal fan drive. The motor speed is 1,100. I think this is 1,000. This is 1,725, right? So that's 1,725 RPM, and the pulley diameter is 127 mm. The power transmitted at the given RPM is 2,983 watts. The arc of contact is 160 degrees, and select the appropriate flat belts and the corresponding pulley to be used. However, I just would like to make some changes right here, because I think we also need some values for the center of distance and also the speed of the fan, because usually if here's the centrifugal fan, so for example, here's our centrifugal fan, right, and here's our shaft, and sometimes the electric motor would be right here or somewhere okay, or at some position or location, and the pulley right here, we have this, let's say we have this pulley, this driven pulley, and here's our driver pulley. Okay, so somehow you would already know the center distance. Okay, so that's my point of adding values for the center distance, because in the design you would already know somehow what's that distance. Okay, so let me draw this in this view. Okay, so here's our electric motor right here, and here's our pulley. Right, so here's our electric motor, right, and here's our driven pulley, or driver pulley rather, and here's our driven pulley. Okay, so my point right here again is that you would already know the center distance. Okay, and you would also know, already know, most likely you would already know the speed, because you want, or you have a specified speed already for the fan. So that's why you should have this n sub 2 as well. Okay, so therefore additional values, or additional parameters are, okay, we have n sub 2, that's the driver, the driven pulley, and let's just say this is 950 rpm. And for the center distance, we have, let's say we have 110 mm. Okay, so that's all, and now let's go to the solution. Alright, so for the solution, number one is to obtain or list down necessary information. Okay, so our the given value right here for the power is that you see here the power transmitted at the given RPM is 2983. So although this seems to be the design power, however, to be safe, I think I just need to increase this, or I just need to, or I'll just assume that this is the rated power. Okay, so this will be P sub R, which is 2983 watts. Okay, again, this is a design problem, so it would be safe to assume, if we use, or if we think of this as a rated power, because we need to increase this, right? We need to multiply this to the service factor. So somehow, if we compute for the belt width, then we can have a longer belt width if we use this as a rated power. Okay, what else? What's given is the angle of contact, which is 160 degrees, and motor speed, that's the N1, is equal to motor speed, which is equal to 1725 rpm, and the diameter is equal to 127 mm, that's approximately 5 inches. And for the N2, this is our additional parameters, which is 950 rpm, and for the center distance, this is 110 mm. Okay, so once you have that, then the next step is to solve for the design power. Okay, design power. Okay, so PD is equal to the rated power times the service factor, and let's check our table. Okay, so this is table 12. Okay, so right here our application is here, fans, centrifugal, and our type of motor, it says a normal torque squirrel cage AC motor. So here's the squirrel cage AC motor, and here's the normal torque, and therefore our value is 1.2 for the service factor. Okay, so let's write here. So from table 12, SF is equal to 1.2. Therefore, PD is equal to 2,983 watts times the service factor of 1.2, and this is equal to 2,983 times 1.2. This is 3,579.6 watts. Okay, next step is to solve for other available parameters, right? And this is what we need. By the way, we also need to assume the type of belt. So let's say use rubberized fabric belts. Okay, so therefore we will need to compute for the belt speed, for the linear belt speed, so which is just V sub B is equal to pi D times the N, and of course we need the N of the faster pulley, okay, which is this is pi times the diameter of the faster pulley, that's 127, right? 127 mm, and this N right here, this is 1,725 revolutions per minute. Okay, so if we compute that, 1725 times, I'll convert this to meter, times 127 times pi. So I have okay, I think I forgot to divide this by 1000, so this is 688, 688.24 meters per minute. And what else? We can also solve for the speed diameter relation, right? So N1 or solve for D sub 2. So N1 D1 is equal to N2 D2. So D2 is just simply N1 times D1 all over N2, and if we substitute all the values, this is 1,725 times 127, this is in mm, divided by 950, and therefore this is 1725 times 127. So this is 230.6. 230.6. This is in mm, approximately divided by 25.4. This is approximately 9 inches. Okay, so the next is this is step 4. The next is step 4. Okay, so select actually this is now about belt selection, so select number of ply. Okay, using which table? So we'll use using table 2. Okay, so right here, here's our belt speed, and recall that our belt speed is 688 meters per minute. Okay, and our D our D sub 1 is I think that's 127 mm. Okay, so right here, this is just the minimum pulley diameter for rubber belts. So how do we know if the 3-ply is enough or the 4-ply is enough? Is actually we can assume if we want this 3-ply, because as the ply number increases, actually the cross section increases, and of course you can get a higher power capacity, but of course that is also tantamount to the cost. Okay, so that's why sometimes, or usually, what we want is just the lowest possible size. Okay, so 688. So we have here, if we use 127 and we have a more fast speed, or a faster speed than the 688, then we can actually use the 3-ply. Okay, so that's the assumption. Again, to use or to determine which ply number you would use for your design, I think it's just an assumption, and you can actually you can still design the width. Okay, so you can compensate which if you have if you don't have that much allowance, then I think you can still compensate it through the width of the belt. Okay, so let's just use three ply. Okay, so select number of ply using table number 2, then we'll just write here use 3-ply. Okay, so the next step, if we have the ply or the thickness, then we can solve for the belt width. Okay, so how do we do that? So using table -1, and recall that the equation is W is equal to the design power divided by this K. That's the specific power capacity of the belt, and times this correction factor. So first, let's find this. Okay, so C theta is equal to 180. So here's our equation, minus 60 times the difference between the two diameters, 230 minus 127, divided by this center distance. Okay, so take note, here's our equation, center distance, and right here is the difference between the two diameters. And if we compute that, what we get is 123.82 degrees, so approximately 124, and refer to table 11. Okay, so here's the table 11, and we just have to go to 124. Okay, so we have here 120, and we have 126. So let's just assume that it's 0.84. Okay, so C theta is approximately 0.84. Okay, and now for the K. And for the K, okay, for the K values, let's go to table 1. Okay, let's write here for K values. Use table 1. Okay, so here's our table, and recall that this is linear speed, and we are going to look at this fabric belt and this belt, this ply number. Okay, so our speed is 688, right? 688, and we don't have the 688 right here, so it's somewhere in between this. Okay, so it's 688, and what's gonna be the k values. Okay, so when it comes to this, I think I mean, for me, I would do interpolation for this. So let's just write 610, and this is 688, and this is BB. Right here, here's gonna be the value for our k, 688, and what else? This is 762. Okay, so I'm just rewriting this, and this is 79, and this is unknown, and this is 97. Okay, I guess I'll just continue this in the next video.